Okay, in this next example, continuing with section 7.3, where we are using the central limit theorem and we just have to decipher which scenario it is, right? So in this example, we have engineers must consider the breadths of male heads when designing helmets. The company researchers have determined that the population of potential clientele have head breadths that are normally distributed with a mean of 6.7 inches and a standard deviation of 1.2. So there are a couple things we need to talk about. So the first thing is looking at some red flags here. The first thing I see, I read, head, hell, breath, yeah, great. And then boom, normally distributed like comes out at me. Like Uma Thurman in Kill Bill, right? Part 2, you know that sound. And then, and with a mean, I don't even care what it's standard deviation. Oh my God, red flags everywhere. My heart starts going fast. I realize, boom, red flag, red flag, red flag. First of all, it's given that it's normally distributed. So part 1 is done. Okay. It doesn't matter what my sample sizes are anymore because it's telling me the population is normally distributed. Part 1 is done. I don't have to do anything. I see the word mean. I see the standard deviation. Mean, standard deviation, mean, standard deviation. Is this a proportion? No. It says mean, standard deviation, mean, standard. This is a mean, right? This is a mean problem. Why? Because they gave us a mean and a standard deviation. Those are your red flags. Now, it doesn't matter the preliminary anymore, but I do know because it tells me it's normally distributed, but I do still have that part 2 with the just giving the sampling distribution. So in this first example, we have suppose we select random samples of size 41 from a population. What is the probability that the breadth of male heads average is more than 7.3 inches? So the first thing I want to do is maybe do like a part 2 away over here maybe and put distribution because I don't want it to really interfere with the problem itself. So the first one was the mean. Remember the mean of the sampling distribution with respect to the sample means, right? So that was given as 6.7. And the second part, the standard deviation with respect to the sample means would be 1.2 divided by the square root of n. In this case, in this particular part, we have a sample of sizes of 41. So we'll have 1.2 divided by the square root of 41. Okay, so now let me go ahead and kind of put this little sidebar. And now we can go ahead and come back to the problem. So the first thing I want to note is that we want to see and draw the curve, right? What are they talking about? So I do know this is 6.7. And if I wanted to label the x-axis as standard deviations away, I would go ahead and put this in the calculator and add it 3 times to the left, right, and then subtract 3 times to the left. I did this ahead of time, so this is going to be 6.51, 6.33, 6.14, and then 6.89, 7.08, and then 7.27. So if I have a sample sizes of 41, right, and I want to see where if I took a random sample of a sample of 41, that the male head's average is more than 7.3 inches. So here I'm looking for the probability that the sample mean of the sample I take of 41 is more than 7.3 inches. So let's go ahead and mark that on the curve. So 7.3, well 7.27 is here, so here's 7.3. And that means if I want more than, that's that is a tail, right? And we can see that that's going to be a very small probability, right? So let's just do what we usually do, right? Normal CDF of left endpoint 7.3, right endpoint, which is 1E99, comma, the mean of 6.7, and standard deviation of 1.2 over the square root of 41. So we can just go ahead and put that in the calculator. We expect it to be really small, right? So second vars, normal CDF, and let me go ahead and clear that out. And the lower was 7.3, upper still is the tail to the right. Clear that out. The mean is 6.7. And here, the standard deviation is 1.2 divided by the square root of 41, the sample size. And we can see here that, again, we have this e to the negative 4. So that means I will have 0.000, and then looking at this test digit 8, it'll be 0.0007. Rounding this to the nearest percent, 0.07%. I'm not sure which answer I didn't request, but I always do both in case mom asks you for either one. So you notice that it's less than a 1% chance. So would this be unusual for me to take a random sample of size 41, and that average of that sample is more than 7.3 inches? Yeah, it would be unusual. So we would say that there is less than a 1% chance a sample has an average head breadth more than 7.3 inches. And then we could say for males or something. I don't know. I'm sure you could word it better. I'm just kind of going on a whim here. But that's the thought, right? Is that it's unusual because there's less than a 1% chance that I would randomly select a sample of size 41, and that average of that sample would be more than 7.3 inches. Basically, males don't have bigger heads than 7.3 inches. Okay, so that's one scenario, and we love when they tell us it's normally distributed. It kind of alleviates a lot of preliminary work, right? Okay, so now in this example, we're going to look at in what range would we expect to find the middle 36% of most head breadths, and we'll round our answer to 2 decimals. So in this case, we have a sample mean still of 6.7, but our standard deviation here is going to be 1.2, and I want to note that it's not going to be the standard error as we know. So let's make a note here. Notice that they didn't give us a sample size like they did in the beginning with part A. So since no sample size is given, we go back to Chapter 6, Methods, or assume n is equal to 1. So you either can divide by the square root of 1, which gives you still 1.2. And so this means that when we do our problem here and find the probability of most head breadths, not the average, but just the most head breadths is between these two values, right? Because if we're looking for the middle 36% here, that means we know it's within one standard deviation, right? Not one standard deviation, because that would be 68%. But we know that it would be somewhere like here, right? Between the one standard deviation away from the left and from the right. So x1 and x2 are not averages of head breadth, but just head breadths. So this means that if I go ahead and label my x-axis, I would have 6.7 here, and then add and subtract one standard deviation, which here in this case would be 7.9, 9.1, and 10.3. And to the left, it would be 5.5, 4.3, and 3.1. And so if I was looking for the middle 36% of just head breadths, notice not averages of head breadth, but just head breadths itself, I'm just looking for this certain number of inches. Okay, so the method will be similar. We still are given an area, and yet we need to work our way backwards to find x1 and x2. So if you recall, we used invnorm. When we were given area, needed to find x values, we used invnorm. And what you did is you just put in the area and the mean and the standard deviation, and then selected the area, and we're going to select center. So if we go ahead and go to invnorm, second distribution, invnorm, right here, number 3, we can put in the area, middle 36%, our mean is 6.7, and then here I would put in 1.2 and select center and paste and enter. So this gives us two values. Let me drag this over. And notice that we have the two values are given to us, which is really nice, right? So if this probability is 0.36, then the two values in which bound the middle 36% is going to be the set 6.14, 7.26. So the probability in which I would select a sample that would have head breadths between 6.14 and 7.26 inches is 36%. So we could say something like, we expect the middle 36% of most head breadths, male head breadths, to be between to be between 6.14 and 7.26 inches. So that's kind of like the interpretation. And again, here they don't mention the averages of samples, so we would assume that it is one sample we're looking at. Now, if I go to now part C, where it says now we're drawing samples of size 57. Now what would be the range of the middle 36%? So it's actually the same process, but instead of n equal 1 and finding values of head breadth, we're actually now having a sample size of 57, and we're looking at averages of samples for head breadths. So this means that the mean of the sampling distribution still remains to be 6.7, but the standard deviation will be 1.2 and then divided by the square root of 57, because n is equal to 57. And the second part that we would do is exactly what we just did up here. But instead, now if we look at the middle 36, the probability that I randomly select a sample, which is a sample size of 57, and that sample size average is between these two averages, that's 36%. So in order to find x sub 1 bar, comma, x sub 2 bar, now we're looking for sample means from sample sizes of 57, in which bounds the middle 36%, we can now use inv norm. And it's going to look similar, but you can expect that the standard deviation will be 1.2 over the square root of 57, but still choose center. And when we do that, we'll go back to second distribution, inv norm, and then just change. I would just come over here to the right and hit divided by, and then the square root of 57. Now remember that as the sample size increases, the standard deviation gets smaller, so that's why we're dividing by that sample size, the square root of the sample size. It's still center, hit paste. Let's see how this makes a difference. So let me drag this over and make it a little larger so we can see. So now we can see that the difference between the two. So the bounds before with just one sample was 6.14 and 7.26, and those were just inches of head breadths. Whereas now our bounds are 6.63 and 6.77, and these are sample means. So we would say that we expect the middle 36% of sample means or averages of size 57 to be between 6.63 and 6.77 inches.